All right, here we want to talk about implicit differentiation, which we'll explain in a later video, but can be really important when it's difficult to solve for x, or when you have a function that's not already in terms of x. It's sometimes easier to take the derivative this way than do all the legwork involved in trying to isolate certain variables. And so I want to talk about why this works, because it gets a little hidden behind the scenes when you're actually doing the mechanics of this method. But say we have something like this, d dx of 3x. So we kind of take for granted, because usually our variables line up, that what this is asking us to do is take the derivative of 3x with respect to x. So derivative of 3x, treating x as the variable, is 3. All right, what if they asked us to take the derivative with respect to x of, let's say, 3y. So notice something a little different here. They're asking us to take the derivative with respect to x, but our variable here isn't x. So what can I do, and this is the part that kind of hides behind the scenes, to actually compute this or make it work, is my 3y part of this I could think of as the derivative with respect to y of 3y. That we could do, right? Because now it's asking us something we know how to do. Take the derivative of 3y when y is the variable. So this we can compute. But notice we don't want to fundamentally change the question. So if we still want it to be the same as what they were asking for before, notice if I add a dy dx out here, if I cancel these dy's, I'm back to where I started. These two things are equivalent to each other. It's asking for d dx of 3y. And so what I'm really doing is using chain rule to my advantage here. I'm making an extra link in my chain because I can do this part as long as I compensate by putting a dy dx over here. And so the derivative with respect to y of 3y is just 3. And so now I'm left with 3 times dy dx. Well, I introduce this piece to make this thing work out. So you don't always write out all of that when you're doing chain rule, so it's a little, or when you're doing implicit differentiation, so it's a little hidden that there's chain rule behind the scenes. So let's look at an example of how we would actually use this. So let's say we had, and this is what, an equation of a circle, x squared plus y squared equals 25, and we want to find dy dx. So if we had this whole thing solved for y, in fact, you can probably see it really quick. We'll do it just so we can see what would happen. If we get y by itself, right, and then take the square root of both sides, and then it splits into 2 because of the plus minus. So we would have y equals. So we would have to do both cases, one for the plus, one for the minus, and you notice there's some chain rule in there if we wanted to find the derivative of y with respect to x. So this might be a little bit hairy, but if we could just leave it the way it was and take the derivative back here, and just get dy dx by itself, it might be a simpler way to end up with the same thing. And in fact, that's exactly what implicit differentiation does for us. So we'll say, all right, I want to take d dx of this entire function, which means each term individually. So I want derivative with respect to x of x squared, derivative with respect to x of y squared, and derivative with respect to x of 25. You can write it on each individual term. Maybe eventually in practice, you might stop writing this out. You know that you can take the derivative of separate terms separately already. But because it's the first one and we just want to see what's going on, maybe I'll be a little more thorough about the writing. All right, so derivative with respect to x of x squared is 2x. Derivative with respect to x of 25, because it's a constant, is 0. So here's our interesting one. I can take the derivative with respect to y instead, which would be 2y, as long as I add my little, I didn't take it with respect to x, my little chain rule piece. What allows me to do that is if I say, this is the derivative with respect to y times dy dx. Because think about when I cancel the d dy, like I did up here, it's the same thing as d dx of the other variable. And so now, since my goal was to find dy dx, all I have to do is get dy dx by itself in this equation, and I've succeeded at taking the derivative of this function, and I didn't have to use chain rule, I didn't have to rearrange the whole function first. So subtract 2x from both sides. So I get negative 2x, and then divide both sides by 2y to get this one to cancel out. So dy dx equals negative 2x over 2y, and obviously the 2's can cancel, so I end up with negative x over y. So there's an example of taking the derivative using implicit differentiation.